But of course, today every rascal thinks he knows the answer, but he is deluding himself. So Einstein is not very clear about photon. Even Richard Feynman also is not very clear about photon. Hi friends, I am Satish Kumar from Belgaum, India. Physics is just manifestation but not creation. So today I am going to highlight a topic that is photoelectric effect, which was published by the great scientist Einstein in the miraculous year 1905. So today I am going to discuss on the queries unattended by Albert Einstein on photoelectric effect. So what I feel that some concepts were not attended by Einstein and some explanations were illogical. That's what I felt. So let us go into the concept first. Photoelectric effect that was cited in Einstein Nobel Prize. In 1887, first Heinrich Hertz and his assistant Philip Leonard, they observed that when light was shone on certain substances, the substances gave out cathode rays, electrons. Only the number of electrons emitted and not their energy increased when the strength or intensity of the incident light was increased. This was the observation by Hertz and Leonard. Next, the observations of Hertz and Leonard were in contradiction with the then established wave nature of light. We all know that at that time Maxwell's theory was in rule, means the light or radiation is behaving like a wave, that is electromagnetic wave, but they could not explain the phenomenon of this photoelectric emission with the help of Maxwell's electromagnetic theory. Then Einstein proposed that light can be rather considered as particles and offered a successful explanation of the observed phenomenon. So in one of the famous papers published in 1905, Einstein explained the experimental observations of Hertz and Leonard and established firmly the corpuscular nature of light proposed earlier by Max Planck. For this, Einstein has submitted the paper in 1905. After 16 years, Einstein awarded Nobel Prize in 1921 for his contributions to theoretical physics, especially for his explanation of the photoelectric effect, and this also brought Nobel Prize to Einstein after Millikan's experiment. With the help of Einstein's equations, Millikan could find the value of Planck's constant, so then it was awarded to Einstein in the year 1921. This is the experimental setup which we have in NCERT textbook, and this is the experimental setup which I got it from Einstein's paper. This is the original setup actually. You can find light source, monochromatic light comes here. This is a monochromator, means a filter will be used so that you will get monochromatic light. Falls on the metal plate, that there is a grid, there is a collector, it is the path is closed, you can find the current in the ammeter. So here the potential difference is maintained here. This is the experimental setup. Next, these are the observations. The first one is the intensity of light and the photoelectric current, how it varies with intensity of light. So variation of photoelectric current with intensity of light is a straight line, because as per the Einstein, photoelectric current is proportional to the intensity of incident light. Number 2, variation of photocurrent with collector plate potential for different intensity of incident radiation. These are the different intensities of incident radiations I1, I2, I3. As the intensity is increased and keeping the same frequency, we found that as the intensity is increased, the saturation current increases. This was the graph we obtained from NCERT textbook, and this is the original graph obtained by Leonard. Here they have taken on the positive axis only, they have shown like this. Next, this is variation of photoelectric current with collector plate potential for different frequencies of incident radiation. So here we have maintained the intensity same for different frequencies. We can see that the cutoff voltages or stopping potentials are different for different frequencies. The same thing here we have shown here. This is the original Lenard graph. That's what I found it from the website. So this is the graph. This is what generally we draw. This is the original graph from the Lenard observations. So when white light is sent through a monochromator and is then incident on a thin metal plate, the incident light is absorbed by the metal plate, which then ejects electrons from it. These electrons are attracted towards a collector at which they arrive, but only if they have sufficient kinetic energy to get past a grid to which a retarding potential is applied as shown in the figure. This phenomenon is known to everyone. That's what I'm skipping the explanation here. The kinetic energy of the electrons emitted from the thin metal foil could thus be gauged by varying the retarding voltage. The plate to collector electron current being measured by an ammeter, Lenard made the surprising discovery of a cutoff frequency, that is threshold frequency. So all these things are known to you friends, but this is the great person behind this phenomenon was Lenard. The maximum contributions to this phenomenon were by Lenard, not by Einstein. Einstein has given only an explanation to this phenomenon, but not the phenomenon. So experimental observations were performed by Hertz and Lenard only. Lenard contributed more for this phenomenon. So what are the Lenard's observations? When a sufficiently negative voltage is set on the grid, the electrons do not reach the collector. Repelled by the negatively charged grid, intensity of light had no effect on the energy of ejected electrons. See here we can see that. See, we are changing the intensity but maintaining the same frequency. You can see that the retarding voltage will be same for the three intensities. You can see here 1, 2, 3. For all the three, the stopping potential is same. This is Lenard's observations. Next, there was a threshold frequency below which not a single photoelectron was ejected. Below this frequency, the brightness of light made no difference. Here you can see that there is a frequency called threshold frequency, above which only the photoelectric emission begins, below which there is no photoelectric emission. However high the intensity may be, generally as physics students, we study this concept under the heading of loss of photoelectric emission. Lenard was an experimentalist of genius. Why I am going to focus on Lenard? Because the main contributions were made by Lenard, not by Einstein, to this phenomenon. The drawback of Lenard was Lenard could not explain the phenomenon, that's all. Right? Lenard was an experimentalist of genius. It is however said that he claimed far more recognition for his investigations than was due. Lenard got many honors, including 1905 Nobel Prize for his work on cathode rays, but he still felt that he was disregarded. This explains why he frequently attacked some other physicists. So Philip Lenard had systematically recorded all the important observations with regard to the photoelectric effect. As we have seen that there were 3 to 4 graphs that we have seen, that they are all from the observations by Lenard. It was, however, Einstein's paper of 1905 in the distinguished journal Annales der Physik, in which he interpreted light as particles that offered a satisfactory explanation of the photoelectric effect. So until Einstein wrote this paper, it was assumed that electromagnetic radiations traveled as waves. Einstein considered the quantization of light into packets of energy called quanta in the context of propagation of electromagnetic energy. So wrote Einstein, according to the assumption considered here, when a light ray starting from a point is propagated, the energy is not continuously distributed over an ever increasing volume, but it consists of a finite number of energy quanta localized in space which move without being divided and which can be absorbed or emitted only as a whole. Means as per this, the energy is not spread, the energy is localized at some places. So So nowadays we are all enjoying the photon picture of radiation. This is photon picture of radiation. This has got quite contradiction with the wave nature. So here the photoelectric effect, we all feel that photoelectric effect was named after Leonard. No, it was named after Einstein, not Leonard. And Leonard never forgave Einstein for this. In essence, Einstein proposed that the incident electromagnetic energy is absorbed as a corpuscle of energy h nu by the metal plate. As a result, an electron is ejected from the plate. A part of the energy absorbed goes to overcome the work function phi, and the residual energy is carried by the ejected electron as its kinetic energy. So this is the famous Einstein's photoelectric equation. H nu is energy of the incident photon, this is work function, and this is the kinetic energy. This is the mathematical form of Einstein equation. Of course, he used conservation of energy here. We don't know how far it is successful and all. As mentioned earlier, the ejected electron is detected at the collector only if its kinetic energy overcomes the retarding potential, that is QVS. Once electron overcomes the retarding potential, then only it could reach the anode plate, otherwise no. So we get the following relation: H nu equal to work function plus QVS. Of course, this is maximum kinetic energy only. So we get an equation for stopping potential, which is H by Q into nu minus phi by Q. This is the equation. This is Einstein's equation in another form. This is also known to all. There is a graph drawn between stopping potential and frequency. You can see this is the equation for stopping potential in terms of frequency. H by Q will be the slope of this line. So from this slope we can find the Planck's constant. So Millikan carried out the first direct photoelectric determination of Planck's constant. Millikan found the value of Planck's constant from Einstein's equation. So he is Robert Andrews Millikan. So until then Einstein was not awarded Nobel Prize. Okay. Next, in essence, Planck had discovered the quantum structure of electromagnetic radiation, but he himself did not quite see it that way. This point is very important. Planck had discovered the quantum structure, but he himself did not quite see it that way, but he who used the quantum picture of radiation more violently, Einstein only. So Einstein used the quantum nature of radiation to explain this phenomenon. Rather, he thought of the new assumption merely as a mathematical trick to obtain the right description of the black body radiation spectral intensity profile. To Planck, his hypothesis was an act of desperation, and he lamented that we will have to live with it. That means even Planck doesn't know whether photon exists or not. Photon existence has become a mystery nowadays. Okay. So the significance of the Planck's constant H remained for him a mystery till Einstein explained the photoelectric effect. The bundle of electromagnetic energy is now known as photon, and therefore the phenomenon observed in the Hertz-Leonard experiment explained by Einstein as Einstein's photoelectric effect. However, the quantum of electromagnetic radiation was not referred to as the photon till 2 decades after Einstein's seminar paper. That's what I told you. 1905 he published his paper. 1921 he obtained Nobel Prize. In fact, it was the American chemist Gilbert Newton Lewis who coined the word photon in a letter to the editor to Nature. So till then there was no word like photon. It was called as a corpuscle of energy, bundle of energy, packet of energy. The first time they used the word photon by Gilbert Newton Lewis. So Einstein's interpretation of the photoelectric effect became a historic building block of the quantum theory. So far this is the first part of my video. The second video will be in the next part. So far I have explained to you whatever the observations made by Leonard, Hertz, and explanation given by Einstein and Millikan, how he determined the value of Planck's constant. So in this video I want to discuss my queries in Q. So these are my queries in Q related to photoelectric emission. The first one, as this phenomenon is less than 1% efficient, all the photons incident on the metal surface would not cause the emission. So the relation between current and the intensity is no longer valid. This is my query. So my query is, according to Einstein, this is the metal plate, this is the anode collector plate, and light falls on the metal plate. Suppose if one photon is incident on the metal plate, it has to eject one electron. Means in order to eject one electron from the metal surface, it requires one photon to be absorbed by the electron. So when the phenomenon is less than 1% efficient, as you see, means not all the photons incident on the metal surface could emit electrons. Then how come we draw the graph between intensity and photoelectric current? That means that for one photon, one electron, one photon, one electron, this becomes no longer valid. Next, query 2. When radiation or light of suitable frequency is incident on a metal surface, it ejects electrons from it. But sometimes radiation after striking the metal surface have chances to get reflected from the metal surface. This was not explained by Einstein. That means, so here sometimes radiation, because we have seen that there are some metallic surfaces, when light falls on the metallic surface, photons might get reflected as light gets reflected from a mirror. Photons also, they might get reflected from the surface. It could happen. This was not properly explained by Einstein. And it was explained that the electrons coming out of the metal surface, normal to it, will consume minimum energy of the incident radiation and hence come out with maximum kinetic energy. The electrons from the inner layers of metal plate will have to consume more energy to get detached from the surface, and as it needs to penetrate through the electrostatic forces, so they come out with less kinetic energy. According to Einstein theory, the electrons coming from the metal surface, you take the metal surface, the electrons coming normal to the metal surface, they will have more kinetic energy, and the electrons coming from the metal surface, suppose the metal is having slight thickness like this. So suppose if photon is incident here, electron of the metal which is very much inside the surface, it also may absorb the energy and come out. So what happens? This will consume more energy to come out of the metal surface. In that case, the kinetic energy of the electron is less. So this is called surface photoelectric effect. When light falls on the surface, then the electrons that are coming from the metal surface, normal to it, they only have more kinetic energy, and the electrons coming from inside the surface, inside the metal plate, so they will have less kinetic energy compared to the previous one. But the thing is, in some of the books I read that the cathode, the photocathode, what we are considering must be very thin, right? Now, so in that case, if I write h nu equal to 5 plus Ke, the Einstein's equation is valid to that photon which could eject electron from the metal surface. As I told you in the query 1, the phenomenon is less than 1% efficient. That means if 100 photons are incident on the metal surface, we cannot get 100 electrons, sometimes less than that also. Then what about Einstein equation? So I feel that Einstein equation is valid to only those photons which could eject electrons. So in that case, some graphs become invalid. That's what I feel. Next, this is a very important query. So in the graph, you see that in this graph, here potential is 0, but there is some current. Hope you are understanding now. So it is very simple for you. 0 potential, there is some current. So there will be current only when the electron reaches the plate. Is it clear? That means when there is no photoelectric, there is no potential difference, the photoelectric current becomes 0. But here what is happening, I can tell you. When here I can consider the photocathode and anode here. This is cathode, this is anode, this is anode, this is cathode. Now I am not giving any potential difference. This is an important query of mine. So when photon is incident on the metal surface, electrons are ejected, right? But there is no potential difference between these two. This is not positive now. Okay, then how come electron could travel only in this direction? Why not into the metal this side? That means when there is positive potential, of course, these electrons are attracted towards positive plate. When there is no potential, why electrons should travel in this direction? This is my query. That's what I have written in this slide. When there is no accelerating potential, why electrons only do travel towards the opposite plate? There is a possibility for an electron to move in any direction, even it could have gone into deeper areas inside the metal. Next, in the graph drawn between potential difference and current for different frequency and same intensity, how would it be possible to have same saturation current for same intensity of incident radiation? Because intensity equal to NH nu by TA. So let us see, this is quite contradicting now. Suppose my question is, if two light sources having same intensity, let us say yellow and red. Yellow is having less wavelength than the red, means yellow will have more frequency than red. So according to photon picture of radiation, intensity means N by T H nu by A, number of photons incident per second per unit area. This is intensity according to photon picture of radiation. So here also I write N by T H nu by A. Let us say area is same, nu is same, then yellow and red. New yellow is, yellow color will have more frequency than red. That means number of photons in case of yellow light should be less than that of red. Hope you understood now. See, yellow color is having more frequency than red because yellow and red have same intensity. So in that case, number of photons emitted per second in case of yellow must be less than that of red. Then in that case, for different frequency, how come the same, if the intensity is maintained, how come the saturation current becomes the same? That means when intensity is same, saturation current also must be same according to the Einstein's theory. But my query is, when we are using different frequency lights, then for same intensity, number of electrons coming out means number of photons incident per second is different, then how come the saturation current is same for all? So this is my query. Once again, when intensity is same, number of photons is not same, because for a given frequency, intensity is proportional to number of photons emitted per second. This is accepted. But when you are comparing two lights, one is yellow and another is red, when their frequencies are not same, how come they emit same number of photons per second? When they do not emit same number of photons per second, why the saturation current remains the same for both? This is the query of mine. Okay, this is one. Next, number 6. According to Einstein, one electron is released on absorbing one photon. That means photoelectric emission is 1-to-1 interaction. But I seen in some books that when an electron absorbs 2 photons, from the total energy absorbed, if we exclude the work function, then the rest will go as kinetic energy, right? See, first of all, h nu equal to work function plus kinetic energy. This is Einstein equation. Suppose if particular electron receives 2 photons, then it will receive more kinetic energy. That means if it is 2 photons, if it receives 2 photons, then 2 into W naught plus K1 is equal to W naught plus K dash you can see that k dash is more than 2k1. That means the kinetic energy of the electron becomes more than doubled when it receives 2 photons. First of all, the main fundamental question is it possible for an electron to absorb 2 photons? Okay, suppose if it is so, according to Einstein, it is 1-to-1 interaction. One electron has to absorb 1 photon, but how come this is possible? When electron absorbs 2 photons, then if we exclude work function, then whatever the remaining energy, it will be given to electron as kinetic energy. If this happens, Einstein said photoelectric emission is 1-to-1 interaction seems no longer valid. This is my query. But on the similar lines, what I want to tell that if one electron is released from the metal surface on absorbing 1 photon, if 2 photons are incident, 1 electron only will be ejected with more kinetic energy. When this is possible, why not 2 photons whose energy is less than the work function? That means I take photon frequency less than threshold, but I consider 2 photons whose frequency is less than threshold. Why not electron absorbs those 2 photons and cause photoelectric emission? Hope I am clear. When one electron is able to absorb 2 photons to cause the emission, why not an electron can absorb 2 photons? When it absorbs 2 photons whose frequency is less than threshold, why not it is possible? So those were my queries. Now coming to my opinion on photon. It's purely my opinion, my perception only, as rest mass of photon is 0, means photon is not available at rest, means you can never see a photon at rest, and photon does not exist at rest. Next, moreover, its radiation so always does flow or propagate. Radiation always propagates. You cannot restrict a radiation to be at one place. Next, in my opinion, photon picture is only a convincing explanation to photoelectric emission so as to match the experimental results. It's only an explanation, but it is not the exact explanation for this photoelectric emission. Einstein's opinion on photon. These statements were not prepared by me. These statements are by these great scientists only. I got this information from the publication which was published in 2006 by IIT Madras. So, nevertheless, Einstein's discomfort about the photon and quantum mechanics is perhaps borne out by continued worries about what the photon is and where it is. From this we come to a conclusion that Einstein himself is not very clear about photon. Next, the famous Richard Feynman, his opinion. Richard Feynman is said to have remarked about whereabouts of the photon that nobody knows, and it is the best if you try not to think about it. Means one should not think about what is a photon, where is a photon, but we have to apply the photon theory to photoelectric emission. It is ridiculous. Einstein wrote, even as there are fresh formulations of the photon position operator, it is worth recalling that near the end of his life, Einstein wrote, all the 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta? Means Einstein himself is not very clear what are light quanta. But of course today every rascal thinks he knows the answer, but he is deluding himself. So Einstein is not very clear about photon. Even Richard Feynman also is not very clear about photon. My conclusion. So I feel the explanation to photoelectric emission needs to be revised by the great physicists in the contemporary world. I would request each and everyone who watches this video to share with all your physics teachers, lovers across the physics community, so that we will get a plausible explanation to this wonderful phenomenon. And my appeal, I would like to state that I personally felt uncomfortable while teaching this phenomenon to my students in these years. I felt sometimes that some graphs were not properly explained by Einstein's theory, I respect all the physicists who contributed to this great phenomenon. At last, I conclude that these are my queries only, these are my personal queries. Perhaps many people might have understood this phenomenon quite up to their satisfaction. If so, please feel free to contact, to share your answers to my queries mentioned above. So thank you very much.